Welcome everyone back to our regular monthly online research seminar, and nice to see those familiar names who are becoming quite regular as well. My name's David Lamb, I'm the Chief Scientist of Foodagility CRC, and I'll be your MC. For those of you who are unfamiliar with the CRC, Foodagility CRC is dedicated to unlocking the power of digital to transform our agri-food sector. Now, the aim of this seminar series, which is a regular monthly event, is to bring to life some of the amazing talent and activities that we have going in our research community. Consider this a departmental colloquial in a way, albeit with a department that encapsulates our 8 university partners and more than 3 state agencies. So whilst our community is domestic, is local, the research amongst our team is of global significance. You're all part of that community, and I'm delighted to see that we've got more than 100 registrations of the research colloquia. And I note that more than half of you are frontline researchers. So before I introduce our speakers, just a little bit of housekeeping from me. First of all, please note that we're recording this session. Our aim is to make a recorded version of the presentation and the Q&A interaction session at the end available to all our registered listeners. We certainly welcome questions, so please use the Q&A tab at the bottom of your screen. Don't use a chat tab, use the Q&A tab. That way those questions will get to me. Whilst it's not possible for you to ask them of the presenters directly, verbally, what I'll do is I'll be constantly trawling through the Q&A tab questions, and I'll then select those and pass them on to the presenters in an interview style format at the end of the presentation. And obviously, if you have questions that are yet to be raised or yet to be answered throughout the course of the activity, certainly feel free to follow up with the presenters after the event. So just remember, log your questions at the Q&A tab at the bottom of your screen, and at the end of the presentations, I'll retail those to the presenters in an interview style, and hopefully we'll be able to answer them for you. Now, today's presentation is really timely and topical. You may be aware that our entire landmass of Australia in its entirety collects about 3 quadrillion, that's 3 by 10 to the 15 litres of water per year. That may sound like a lot, and don't forget 2019 was the driest year in the 119 year of records since 1900. In agriculture, mining, heavy and light industry, we account for a large proportion of that water. And to keep ourselves alive and to preserve our amazing environmental conditions and the biodiversity we have in this wonderful landmass, every drop counts. You may not be aware that the average water scarcity footprint for an Australian adult on an average diet, what that means is how much water has to be moved around in order to satisfy our food intake, is about 360 litres of water equivalent per person per day. What that tells us is where we grow our food, where we process our food, the water we use to live and consume our food needs to constantly be moved around from where it's fallen and captured to where it's needed. That tells you a lot about how important water is and how expensive it is to actually move and manage. The quality and quantity of water is absolutely central to our existence, and in a country like Australia, more so, given that we've just emerged from record drought. So let me tell you a little bit about our speakers. The topic of today's research presentation, with its evocative title, is Reflections on Water, a Statistical Learning Perspective. And I'm delighted to be able to introduce our 2 presenters. Kerrie Mengersen is a Distinguished Professor in Statistics at the Queensland University of Technology in Brisbane, QUT, one of our founding partner universities. In 2016, Kerrie received the Statistical Society of Australia's Pitman Medal. This is the highest award presented by the Society, and if you don't mind Kerrie me adding, the first time it was ever awarded to a woman. Kerrie's research interests are in mathematical statistics and its application to substantive challenges in health, environment and industry, with a particular focus on Bayesian methodologies. Our co-presenter is Associate Professor Erin Peterson, also from QUT. Erin's an expert in environmental spatial modelling, particularly in stream networks. Prior to coming to QUT, Erin worked as a postdoc research fellow and research scientist and senior research scientist at CSIRO in Brisbane. From 2012 to 2014, Erin also led the Environmental and Agricultural Informatics Monitoring and Indicator Analysis team. Indications are important. Erin will be contributing to the presentation today on the segment on water quality anomaly detection. So it's with great pleasure that I introduce both Kerrie and Erin to share their reflections on water. Thank you.
Thank you very much, Dave. And thank you very much to all the people who are listening. I'm just going to share my screen, so bear with me for a minute. Can you see my screen?
Yes, Kerrie.
Thank you. Okay. Just bear with me for a sec. Okay. All right. I'll just check with the sidebar. Is that okay? Can you see the sidebar or not?
No, we're good, Kerrie.
Okay.
Presentation.
All right. Okay, good. Thank you. Okay, well, thank you very much, everybody. I'd like to first acknowledge the organisations that have funded this work and with whom I collaborate on this work. So this is our ARC Centre of Excellence in Mathematical and Statistical Frontiers, which brings together research in maths, stats and machine learning across the areas of healthy people, sustainable environment and prosperous societies. It brings 7 universities across 4 states and has about 100 researchers and about the same number of PhD and master's students. We also have our QUT Centre for Data Science, which includes core research around bringing together people in a broader range of topics. So statistical science, computer science, information science, and then our data science at QUT, which covers then or the domains across QUT that use data science. So business, health, agriculture, environment, and so on. And then our third layer, which is our external engagement. So this is our Australian Data Science Network, which connects the different centres for data science like ours around the country. So there's about 20 centres in data science that are partners in this Australian Data Science Network. And then our key partners, our external partners with whom we have good relationships and projects. So that's our centre at QUT in data science, and through that centre then we have created a collaboration with the foodagility in the form of a constellation. So we have our advanced artificial intelligence in agriculture, and so the challenges in this constellation are around data, the utility of data, the quality of data. The challenges are also around the analytic tools. At the moment, these are disparate and really fit for purpose, but not necessarily the purpose that we need them for. We also need intelligent methods so that we can have adaptive feedback and learning systems and really, truly AI systems. And also then to have to be able to meet the demand for capability and capacity in data science and data analysis. So the constellation then is looking to address those challenges through creating an integration of the different solutions that are already available in terms of analytic tools to then identify the gaps in those available solutions and to invent the tools that are required to fill those gaps in AI, and then to look to automate those systems so that they can benefit the members of the foodagility CRC and the broader ag community, and then to develop processes for learning. So how do we create learning amongst ourselves, amongst the community, and also between these tools? And so our foundation partners are also listed here, and we're hoping that we can increase this collaboration and expand the partnerships as well. So if anybody's listening and is interested in talking about this constellation, then I'd be delighted to talk more about it with you. So I'd like to talk today about reflections on water. And this is the sort of a once in a blue moon type talk. So I thought I'd show my blue moon photo. And I want to talk about 5 things. And so I thought, well, you know, let's talk about 5 things. I've got 5 fingers, A, B, C, D, E. And I'm going to talk about anomalies, Bayesian networks, citizen science, design, and experiments. And so this is a real romp through these topics in the available time. Happy also to talk in more depth if you're interested. Now, because it's a reflection, I'm going to talk not in so much these orders, but I'm also going to just focus on particular topics in this. So I want to, in anomalies, I want to look at low-cost sensors in stream networks, for Bayesian networks, complex systems models. How do we develop these for, in this case, seagrass resilience, but they could be for a whole lot of other kinds of topics around recovery and resilience. For citizen science, how do we use the new types of technology that we have and information that we have through citizens to, for example, improve predictions of the health of the Great Barrier Reef? And D for design, even if we can collect all of these data, do we really need to analyze it? Can we be smart, or can we have intelligent data collection? And finally, E for experiment. And so I'd like to talk about space-time depth models that we can develop to be able to analyze our experiments more completely, and also then to be able to analyze observational data in these larger dimensions. So because we're in a reflection, I'm going to start with E and then go A, B, C, D and end up again at E. So let's get going. E is for experiment. And so first I want to think about this field trial, and talking about water, the question here is going to be, what cropping system will maximize water use for grain production while minimizing leakage below the root crop zone? So this is a photo of current wheat stripping in New South Wales. It's just been completed. And so this is a really relevant question, as Dave was saying, for the last few years and also for this year. So in this case, then we have a number of treatments, 9 different treatments across different kinds of pastures and different kind of cropping regimes that you can see here. And then we have our data, which is going to be moisture measurements taken at different depths across the spatial regime. So this is a lattice design, typical kind of experimental design for these kinds of studies, and they'll be unevenly spaced. And so we have some challenges then around the large data set in space, depth and time, and high order correlations over all of the dimensions. And what we want to understand is what's the effect of the treatments, but also what are the depth profiles. And so we want to understand about these non-linear depth profiles or splines for each of the site treatments. We want to understand about that for depth, but remembering that depth is going to be measured with error as the soil moves. So we want to account for that error. And we also want to allow for spatial correlation at each of the depths. And so we're going to have a layered model where we have a spatial relationship between each site and its neighbours. So in the little figure here, the purple site is going to be like its neighbours, the yellow sites. And so we can take into account that spatial information in our model. So Y is going to be our water measurement, and we're going to have it as a function of depth. We're going to take into account the spatial relationship at each of the depths, and we're going to have some residual. So if we do that, then fitting these kinds of models in a Bayesian framework allows us to really have a very flexible modeling system where we can try to understand what these depth profiles look like with some uncertainty. And then we can make probabilistic statements about the comparisons between the different treatments. For example, as you can see in the bottom table here, we get probabilities of the differences or the contrasts between the different groups. And so what we can gain from this kind of analysis, just this is a summary of what we've seen, we can obtain the depth trends and the uncertainty. We can adjust for measurement error in the depth, and we can also obtain these probabilities between the treatments. We can look, what we find is large differences between pasture and cropping. We find really nuanced differences between response cropping and fallow cropping at the intermediate depths, the depths that really matter. And if we're just looking amongst the cropping treatments, we can understand more about when we could recommend response cropping. So these kinds of, I wanted to set the scene with this experimental system because it's such a common kind of fundamental design. And these kinds of models then, where we can incorporate spatial effects, we can incorporate measurement error, we can get uncertainty about our estimates, are really important when we try to understand and gain insights from these water-related problems. So we can now go to the second part, which is A, and this is for anomaly. And so I'm going to hand over to Erin to talk about anomaly detection. So over to you, Erin.
Okay. Do you want to stop sharing your screen?
Yep.
Okay. Hold on. Okay, can everyone see that?
Yes, there is a sidebar on the right-hand side, but yes, we do see a slide.
Huh, that's too bad. A slide bar showing the other sides?
No, export, compress, organize, etc.
Okay, hold on.
It's good and clear though, Erin, so.
Okay, I'll go ahead. Okay. Hopefully that got rid of the sidebar. Let's see here. All right, so like David said, I was an associate professor at QUT, and now I'm an adjunct associate professor there, and I have very recently started my own consulting firm, but I'm still working on this ARC linkage project that Kerrie asked me to talk about today, and I can still be reached at my QUT address. So, I think everyone is quite excited about sort of the idea of low cost in situ sensors and how it can improve water, air, and soil monitoring and management. I mean, some of the key things are that going out and collecting a sample and then analyzing it in a lab is quite expensive. And we have big areas that we need to monitor. And so as a result, we tend to have just these little dots. I think of it as like a piece of Swiss cheese where we only know what's going on at a single point in space or a single point in time. So these in situ sensors, I'm obviously going to be focusing on water, produce these high volume, high velocity data. And so, you know, this obviously gives us a chance to really look at, you know, how we're understand processes at really fine temporal scales and potentially even fine spatial scales, so that in near real time. And I would say that to date, most of the focus has been on the kit. So developing the hardware, you know, data storage for these massive data sets, and so, to some degree, the platforms where we store those data. You know, and maybe less focus has been on how we analyze those data. And so with this, these in situ sensors, especially in rivers, the data are prone to errors. So it could be miscalibration. Biofouling is a huge issue for sensors in rivers. It's not such a big deal in sort of air quality or even in industrial applications. And then we have the normal errors around batteries dying and other technical errors. So you have this really error-prone data, but manual detection of these errors is, you know, that defeats the purpose of why we're doing this. You know, that becomes a bottleneck. So you can't use the data to its full potential. You know, there's definitely a need to create this automated data science pipeline because we want regular data, comprehensive, and we need to trust the data quality. If we can move to in-situ sensing, it has the potential to dramatically decrease the cost of collecting data, and we actually get more data in space and time. But even more than that, even if we can get past sort of the anomalies, we need to be able to turn that data into information to make better decisions. And that could be providing landholders with real-time feedback about how they're actually doing so they can adapt their management practices in a timely manner. It could be used to identify sources of, let's say, sediment and pollutant loads, or assess the impacts on freshwater and marine system. So there's a whole suite of really critical needs that this in-situ sensing can support. So that was sort of the motive.
Erin,
Yes?
Are you advancing slides?
I am. Are you guys not
We're on
seeing
the
it?
first slide.
All right, I'm going to quit sharing and reshare. Hold on. They're beautiful slides. I wish you guys could see them. Let's see. Okay, let's see. So can you see a slide with partner organizations?
Yeah.
And can you see the needs and challenges slide? Okay. All right, so that was the motivation for this ARC linkage that we had funded. It runs from 2019 to 2022 in partnership with the Queensland Department of Environment and Science, and also Southeast Queensland Healthy Land and Water. And this project was really built on successful research partnerships that we had with them before through ASIMS. So some of the research providers that you see here are at Monash and RMIT, as well as University of Powell, also collaborators through ASIMS. And then we've expanded to include University of Alaska. Other collaborators that have come on board since we had this funding are the U.S. National Ecological Observatory Network and also the U.S. NOAA. So it's quite a big team, and I'm only going to skim across the top, just sort of make you aware of the research that we're doing. So there's 4 sort of research activities in here, and today I'm just going to talk about the first 3. The first one is to investigate water quality relationships. Second is to look at anomaly detection. We have space-time modeling on streams. And the fourth one, adaptive sampling, is really about where you put your sensors, because you still can't measure everywhere, even if you can do it more densely in space and time. So the first stream, investigating water quality relationships. I obviously didn't do all this research. So at the bottom of these slides, you'll see the collaborators that are responsible, and the little star is the postdoc who did most of the work. So Claire's been looking at this question of whether a combination of lower cost water quality variables could be used to predict nitrate. So a nitrate sensor by itself is about $18,000, but nitrate is what a lot of our collaborators are most interested in because they're interested in nutrient and sediment loads. So Claire's been looking at nitrate at 3 different NEON sites, and she chose those in the US because they're in different climatic regions. So this part of the project is really looking at what are the relationships between multiple water quality variables at a site, and do those change by climatic regions? And what sits behind this is the desire, okay, if we have a nitrate sensor that's out and we have an error and it stops recording, can we use those other variables to infill the gaps? The flip side of that is, if we can't afford to put nitrate sensors everywhere, can we put these lower cost sensors in other places and predict nitrate based on those relationships? So she's been working with general additive models with an autoregressive term on the residuals. And as you can see in the plots below, the one on the left is the modeled nitrate versus the measured. So what you want to see is a one-to-one relationship there. And so you can see that those predictions very closely reflect the nitrate that we see. And then also with each of these predictions, we get an estimate of uncertainty. So on the right-hand side, what you want to see is that those predictions, are the real values, fall within the bounds. And so you can see there with those black dots that, in most cases, those uncertainty estimates capture the true value. So that gives us confidence that when we're making predictions in a place where we don't have data, that we have captured that true value fairly accurately. And she's getting good results across all the different regions. And so that's quite promising. The second stream is around anomaly detection. So this builds on a successful project we had a couple years ago, working with Des, looking at detecting these errors. And, if you've never looked at these in situ sensor data, it's actually quite surprising how many different types of errors there are. So you get these very large sudden spikes. You can get sudden shifts, or like where they've calibrated it and you get a sudden jump in the data. For the streams, a really tough one is drips. So you get biofouling and it just sort of bumps along down. So it's not just one type of anomaly. And anomalies here, we consider those technical errors with the sensors. And so in the first project, we were able to come up with methods that captured what I would consider the easy ones. The things like the sudden spikes or areas where it drops below a real value of what the sensor could detect. We've taken the next step and we're really trying to tackle some of those tougher ones. And what we're doing is we're moving into space. So we're using, at this point in the research, 2 sensors to try to determine whether data at a second sensor can help us detect anomalies at the first sensor. And so Pusala's from Monash has been working on this, and has a pair of sites, so upstream and downstream, where she has turbidity, water level, conductivity, temperature, and they're about, I think, 500 to 700 meters apart. And so she's developed methods to estimate the cross correlation between the upstream and downstream site that accounts for the time lags, because, obviously when you see a nutrient or sediment value change at the upstream site, it takes a while to observe it at the downstream site, and that can change at different times of the year. So essentially what she's doing is, after she estimates that cross correlation, she uses GAM models to predict at the downstream sensor, and then she can compare what you would expect at the downstream sensor from that prediction to the observed value and use that to identify anomalies. So this is a work in progress, and the idea is then to move on to a branching river network, but I think that these results are quite promising as well. The third activity is around spatio-temporal modeling. And so the real question we're trying to address here is, can we use these data, the relationships between water quality variables, after we've cleaned for anomalies, can we actually predict densely in space and time? And this is challenging for a number of reasons. So on the left-hand side, you see a river, a stream or river network. And when you predict along a river network, you need to account for the fact that the topology of the network, the directionality of the network, because you have water flowing from upstream to downstream. Sometimes you have very small tributaries coming in versus 2 large rivers converging. And so you have to account for that sort of disproportionate influence that upstream sites can have on downstream sites. And also, if you look at sites 2 and sites 3, those might be very close in geographic space, but they might not be related to each other at all in sort of a stream network because water doesn't flow between them. So the second issue and challenge, I guess, here is just the data volume dramatically increases. So this is a water temperature data set from the US with I think there's about 250 locations over 5 years. And so you can imagine these massive data cubes where these sensors are collecting data every 5 minutes, 15 minutes. So it's just a massive volume of data that we're working with. So Edgar Santos Fernandez at QUT has been primarily responsible for this. And so he's developed adaptive Bayesian space-time models for stream networks. So he has predictor variables in the model that we represent things that we know affect stream temperature, like air temperature. And he's able to capture the unique spatial relationships in those rivers based on covariance models that we developed in previous studies based on moving average functions. And then he's actually accounting for the temporal correlation at a site, because what you observe now is dependent on what you observed, at previous time steps using vector autoregression. And he's developed a whole suite of different models to account for that temporal autocorrelation differently. And so essentially, he's able to go from this top left-hand panel where you just have locations and observations. You can see in the top right-hand panel, the predictions are very, very, very accurate. And he can interpolate based on that model to create predictions across the network. And because it's a Bayesian model, he can look at exceedance probabilities, which is really, if you're the probability that you're going to exceed a water quality guideline, or in this case, temperature. So there's a lot of really valuable extra information you get from these Bayesian models. So that's just sort of a speed overview of what's going on in that project. We're about 1 year in with 2 years to go. It's worth noting that output of all this is that all of the methods that we develop will be provided as open source software. So that'll be the multivariate anomaly detection algorithms, computationally efficient spatio-temporal models. And I didn't talk about the novel adaptive sampling designs. We have a new PhD student who just started working on that. And so really, it's just the applied outcomes are just to help our partners get to a place where they have a clean and trustworthy data set, improve scientific understanding of the processes, provide some guidance on where, if you only have a certain number of sensors to put out, where should you put them for optimal prediction? And really, I guess just to stress that this is not a Queensland problem or an Australian problem. These are challenges, critical challenges that people are experiencing all over the world. Maybe with that, I'll turn it back over to you, Kerrie.
Thanks, Erin. Okay, so I'll share my screen if you unshare yours. Can you see my slides? Yes?
Yeah,
okay, so I'm just going to do a quick romp through the BCD parts now. So this is B. So we're up to done A with anomaly detection, and thanks to Erin, that's such a fantastic presentation. And I want to talk now about more complex models. So how do we take more complex factors in a complicated system and model them in this sort of Bayesian framework? So now we can think about Bayesian networks. And the context here is when we have an intervention like dredging. So the question now is, how do we look at resilience and recovery of seagrass in this case, but it can be many other outcomes, and an intervention like dredging. So to dredge or when not to dredge. And so we're going to think of these Bayesian networks as almost like a conceptual model. A response, what factors affect that response, what factors affect those factors, and we draw up this conceptual model and then we quantify it. So we say we get data, we get literature, we get model outputs, we get expert judgment, and we probabilistically quantify this complicated system so that then we can flow those probabilities down through the network. And when we do that, then we can look at problems like what's the impact on chute density and recovery and resilience from a bunch of different factors. And in this case, then we can build up each of those nodes with even more detail and take another node and build it up as well. And because we're looking at each of the components separately and then putting them together, and the probabilities connect, then we can then quantify different aspects of the model and then combine all of the probabilities together. So we have these quite complicated models developed from this quite simplistic approach of conceptual model and then the different data that's informing it. And when we do that, we can get results like this. So we can look at, for example, running these probabilities through the model. We can say, what's the impact on the realized chute density, or the loss in chute density, or the rate of recovery, and so on. And so what does that look like over months? And so we can start to see the impact across months. And then we can put all of that together and say, for each of the different seagrass species that you see across the rows here, for each of the dredging regimes, the interventions that we impose on that network model. So for example, if we have no dredging, or if we start in month 1 where we have just 1 month of dredging, or month 2 where we have 2 months of dredging, and so on, and we have different periods of dredging with different periods of no dredging, so we interact those, so we have different kinds of regimes. What's the impact on the resilience and the recovery for the different species? So for example, the pieces of the pie here tell us about the months that it will take for the seagrass to recover, and the outside circle is the resilience, the overall resilience. So we can see here different kinds of impacts under different kinds of dredging regimes. And by doing this, what we've shown in this modelling approach is that if we take ecological windows into account in a dredging regime, we can use these kinds of models to enable up to a 4-fold reduction in recovery time and a 35% reduction in extinction risk. So these kinds of models can be really powerful for these complex systems where we want to understand an intervention. So I come now to C. So C is for citizen science. And I want to talk about these different kinds of data sources that we have. We've been using virtual reality, we've been using drones, and we've had great fun with these different kinds of data, and how do we extract the information, the insights from those different data sources. And one of the data sources is citizen science. So the project that's really sparked a lot of this work is our virtual reef diver. It's an online barrier reef that has different sites have been monitored for a long time over the 2,300 kilometres of the reef, but there's a lot of water in between those monitoring sites where we don't have information. So how do we get information from those sites? Well, there's any number of divers out there with their cameras, underwater cameras, so let's take their photos, geotag it to a virtual reef, and that's part of citizen science, providing the data, but we do more than that. We ask our citizens then to take those images and annotate them, to whether it's coral or not, and then we can use that information in our statistical models to build better predictions of the health of the overall Great Barrier Reef. So we're using then citizen science in different ways to contribute images and to annotate the images. So we go from elicitation to model to prediction, completing the circle. And what we can do importantly in this is understand, and we model then the citizens' accuracy to improve the credibility of these kinds of data. So we can understand the citizens' accuracy or their ability, taking into account the difficulty of the task and other factors. So you can see in this image here, the marine scientist versus other citizens, how accurate they are. And then also we can try to estimate their ability and compare it to their proportion of correct classifications. And so we can really start to understand which citizens are good at their job and which citizens might need extra training or support. So citizen science can be a game changer. It's a huge area, but it needs to be credible. And now we can estimate the user ability, accounting for task difficulty. We can elicit information using different forms of data extraction methods, virtual reality, MTurk, etc. And we have scalable methods. And I want to finish just with D for design. So D for design, what I want to talk about here just very briefly is that we're coming back now full circle to the more traditional experimental methods and the more traditional statistical methods. We have huge advantages in machine learning, AI techniques, statistical methods, but if we have, and data, but if we have a specific question, we don't need to analyze all of the data. We can think about our big data set, and then we can extract out the data points corresponding to an experimental design that will answer our question. So we think of our question, we design an experiment, what would be the ideal experiment to answer that question, and then lay that experimental design down over our data and extract those points. And we can do that in an adaptive manner, so we can extract optimal points to maximize the estimates or the outcomes that we want. And if we do this, just to show an example, in a model for financial risk, we have 1 million records. If we have this kind of setup, just as an example, then we can look for important covariates, and we can also want precise and accurate parameter estimates. To do that, we only need to analyze, under this approach, 3% of the full data. So instead of analyzing all of our data with all of the hairs on it and poor quality issues and so on, we can extract 3% of the data and answer the questions we want. So we're exploring these kinds of methods, going around then back to an experimental design situation. So we've been through the A, B, C, D, E, and we're moving from the old ways that we think about water and water collection. This is a picture of my grandfather's water truck. And then we go through to the new ways of thinking about water collection with all the new forms of data that we're all excited about analysing, and bringing together new and old methodology to be able to improve the way that we think about water. Thanks, Dave. I'll leave it there.
Thank you, Kerrie, and thank you, Erin. We have a few questions coming in, and again, everybody, if you have a question you'd like me to convey to Kerrie and Erin, please go down to the Q&A tab and fill it out. So there's two questions at the moment. The first one, I believe, is for you, Erin. When you were showing the nitrate prediction work in your presentation, the confidence interval of your predictions range from about 1.5 to 3 micromole per litre. The question really is around, what does this range mean in terms of management? Is this confidence interval acceptable for using those predictions from a management perspective? Did you have any comments on that?
Yeah, well, I'm not an expert when it comes to nitrate, but my understanding is that that's a pretty relatively small error around that. I guess in this particular example that I showed on the screen, that might not be a large nitrate value. And so, does it matter when you're estimating something like loads? Probably not, but it's, our focus is on developing the methods that are going to work no matter what that nitrate value is. So we were just excited that we could predict nitrate.
Cool. Thank you, Erin. A question for Kerrie. The complex Bayesian models, how prone are they to error, given some of the cells will be sparingly filled with actual data in the real world?
Yeah, that's a good question. So we can take that into account in some way. So some of the data will be based on expert information. Some of it will be based on quite sparse observational data. Some of it will be based on quite good observational data. And some of it will actually be informed by models that can sit behind. So you might have like a dynamic systems model or something which is going to sit behind that, that node and feed the results into that node. So when we have data that may be dubious for some reasons, then we can actually incorporate that in the probabilities of the node. And also we can do some sensitivity assessment. So we can say, what if, so for example, if it was your judgment, Dave against mine, and we were at odds with what those figures should be in there, then we could run the model under your beliefs and under my expert judgment, and then we could see what the results were at the end, what impact that made on the bottom node. What we find often is that we can have an argument around one node, and in the scheme of things, when we actually look at what impact it has on the outcome, it's not a lot. And so then let's put aside the small stuff and worry about the big stuff. Or it might be a lot, and then we need to resolve the issue. But what's interesting here is that we actually have the ability to do that in this modelling system, and also it's quite transparent about what we're putting where.
In fact, it sort of follows on to the next question, which I think is dear to the heart of every experimental person, especially in precision ag, and that's your D for design. So in the ideal experiment scenario you laid out, I mean, you used, for example, the financial data, which you had a massive amount of data, and it was really a case of, well, how much do we really need? What happens when you march onto a field and the background photo had a crop, for example, and from a perspective of understanding variability in crop performance or constraints and so forth, in the absence of knowing what the variability really is until you start collecting data and looking at it, what's the prime tactic to bring to bear when it comes to deciding, well, just how much should I sample that field?
Yeah, that's a good question. So there's a lot of work around adaptive design at the moment, and here at QUT we have some people that are some researchers here who are experts in that field. So Chris Dravandi, James McGree, Helen Thompson, and so these people are working on different methods for when you may start to collect the data, and then as you understand the variability, as you understand the data, the outcomes that you're getting, the responses that you're getting, then you can start to say, okay, where should I put my next design point in order to be able to optimize my estimates? And so you start to be able to adaptively collect information, and you create these sort of adaptive designs. And it can be shown that that's really quite efficient. So you might start out with just a simple design, and then you adaptively choose where you need to put the next data. Now that's, I'm doing a lot of hand waving there because this works in quite complex systems, but for a lot of practical situations, you need to have a multi-pronged approach. So it's good to have a sort of a traditional design and then have this adaptivity over the top of that. And also to understand that, there's variation at different spatial scales. So a lot of it depends on, what do you want to actually model this for? What kinds of outcomes do you need? So for example, what you might want to understand within a paddock might be quite different from what you want to understand across a property. And so, the variability or the spatial scale that you then want to, design over or make inferences over or make management decisions over can be quite different.
Thanks, Kerrie. I note that more than a third of our listeners are edu.au, so we're in the education sector or the research sector, universities. So there's a question here from a teaching perspective, if I may. So I might catch you both out, Erin and Kerrie, but do you think we're teaching our data science students enough about the importance of good experimental design and statistical analysis?
Good question.
Short answer.
Erin, do you want to speak to that?
Well, I mean, I can only speak, I wasn't trained as a statistician. So, when I went to school, I would say no, we didn't teach enough. And what I did learn about design is almost the exact opposite of what I know now. So with these in-situ sensors, spatial dependency and temporal dependency isn't your enemy. So in the past, we always wanted to spread our sites out to make sure there was no redundancy in the data, but actually having that spatial and temporal correlation is what allows us to predict in areas where we didn't sample. So it's this whole different approach to design where instead of we're taking a random-ish sample across an area and making an inference, it's the flip side of that is we're going to set our points out optimally, and we're going to use a model to predict. And so it's really a different approach, which I think we're going to see come into its own, because now we are not dealing with sparse data. We have the luxury of having a lot of data. And so my hope is that, you know, maybe we don't have to teach all of that, but at least give people a taste of it, so they're not afraid of spatial dependency and start removing data, which actually is of huge benefit to them.
Thank you, Erin. In fact, there's a follow-up question came hot on the press of that one. So going back to your water sensors one. So how important is spatial autocorrelation for water sensors? If you train models on sensors grouped in one location, so this is getting to your point, are the predictions more accurate applied to a sensor in close proximity compared to a distant location? What's your experience from water perspective?
Yeah, so well, it depends. So with the temperature is almost the perfect variable to predict, because it's strongly related to predictor variables, but then it also has very strong spatial correlation in rivers. So, you know, a lot of times you see spatial correlation up to 1 kilometer. With dissolved oxygen, it may change over, you know, 100 meters. So the ability to predict in areas where you didn't sample has to do with how big of an effect your predictor variables have. So things like elevation or air temperature, and then also how strong that spatial correlation is. So when you have spatial correlation, it knocks it out of the park. Like, the predictions are so much more accurate. So we fit non-spatial models to the stream's temperature data, and you know, we might get an R squared between observed and predicted of like 0.5, 0.6. With just a spatial model, we get 0.9. And now that we bring in this temporal correlation, you know, we're getting like 0.98. So it's really, when you have it, you want to use it, because that's what allows you to draw those maps. And what I didn't show is the space-time models, statistical models, give you uncertainty estimates. So that map also shows you how sure you are, because like that question sort of suggests, as you move away from where you have data, or you get to places where the predictor variables are really different than what you observed, the uncertainty is higher. So you always want to be looking at the uncertainty estimates to know where you can trust the model and where you can't.
Thank you. Good point. Keep an eye on the bathwater as well as the baby.
Yes.
Ladies and gentlemen, thank you for your input. I think we've just about come to the end. Erin and Kerrie, thank you both for your presentation. Please feel free to reach out to Erin and Kerrie. Sorry, there's one more comment. I'm going to pass it on because it's from a student, I believe. I'm just about to finish my grad dip in data science. Based on what you said about what we are taught, I'd agree with you, especially with experimental design. Thank you. So I guess very briefly, given we only have a minute, what areas of data science and statistics have you found to be the most prevalent in agriculture and environmental, if you could bin them together into gross areas, gross classes?
Well, I think it's really in a state of change, isn't it? Because I mean, you have your traditional methods, but also don't forget that those traditional methods are really good foundational skills. And so, what have you been taught there? Then, as long as you're able to think of them as the foundation, and then you can build on them. So, I mean, what we're seeing now is traditional statistical methods being augmented by machine learning methods and AI methods, and that's creating this really really cool and exciting and enabling toolkit around for statistical analysis, taking into account the spatial and temporal nature of data, and really understanding how we can capitalize on that is really important. Having an ability, if you're thinking of how to get into this, understanding the statistical methods and the AI methods and machine learning methods, data science, understanding how to code, like learn to code and learn to communicate.
Awesome. Thanks, Kerrie. And any follow-on comment from that, Erin? Happy with that?
I guess just specifically in the agricultural spaces, don't discount how important that agricultural knowledge is. So the idea of just applying statistical methods blindly to a problem, you really need to bring that knowledge and the data science skills together. And that might be two people working closely together, or one person just happens to have that knowledge, but I think you'll go off the rails pretty quickly if you don't have one or the other.
Cool. Thanks, Erin. Look, thank you all again. Now, of course, next month is our final monthly seminar for the year, and we have Christmas well and truly on our mind. That was a Freudian slip. So think Christmas and seafood. So our next presentation is going to be on the 8th of December, and it's going to be delivered by Professor Renping Liu and the team from UTS on our Sydney Fish Market project, which is just finished. And if you think of everything, data innovation and fish, electronic noses for fish freshness, image-based species identification, and blockchain tracking from catch to consumer. We'll be hearing about that next month. So keep your eye on the call out. In the next day, over the next day or so, we'll bin this recorded or bundle this recorded presentation together and send you all a nod so you can watch Kerrie and Erin to your heart's content. And of course, if you'd like to present to a seminar like this, please let me know, Dave Lamb at foodagility.com. So on behalf of all of us, thank you, Kerrie and Erin, and thank you everyone for your engagement this afternoon. Have a great weekend.
Thanks, bye.